All right, guys, last video right here, and hopefully I'll be back with y'all pretty soon. On that first day back, we will be taking a quiz. I am going to allow you guys to work together on that quiz and also use all of your notes and any of your written notes and homework on that quiz. So it's going to be one that's hopefully a good one for all of you. But in this video, we're just going to have an additional practice problem here at the beginning, and then I'm going to talk about something called modeling, which is basically working backwards. So instead of me giving you an equation and telling you to graph it, I will give you a graph, and I will ask you to write the equation. So we'll get to that here at the end of the video. But let's go ahead. So this is kind of a warm-up problem. So once I write it down, I'm going to encourage you to pause the video and try it on your own. But I will also explain it here in the video. So let me write it down. We're going to try to graph this, and we'll see how you do. So this is f of x equals, let's try 6x to the fourth plus 13x cubed minus 17x squared minus 5x plus 3. Okay, so I'm going to pause the video right now, and I will let you guys try it. So let's see how you guys do. All right, so assuming that you pause the video, remember the rational root theorem says what we do is we do x equals plus or minus. We take all of the factors of the constant, which in this case are going to be 1 and 3. Those are all the factors of 3. And we divide it by all the factors of the leading coefficient of highest degree, which for us is 1, 2, 3, and 6. So this gives us a list of all of the possible, not actual, but possible rational roots of this function. And we're going to go through and we're going to test them. And we're seeing, hey, when I divide by the factor that would cause this rational root, do I get a remainder of 0? If I do, great. If I don't, toss it out and move on to the next one. And remember, we want to move in good logical thoughts here. So I'm going to start. 1 divided by 1 is 1. So I'm going to start by testing x minus 1. And then I'll also test the negative of that. So I'll try x plus 1. And then what I see a lot of students do is they'll just make this list and they'll be like x minus 2 and x plus 2. Guess what? If you choose to test these on this is a dumb move. Don't test those on this problem because there's no 2 up here in the top so that I can't get 2 over 1. Okay, so I should definitely not test anything divided by anything with an x minus 2 or an x plus 2 because there's no way it's going to pop up. There's no way I'm going to get an answer like that from this list anyways. Now I could test x minus 3 and or x plus 3 because I do get a 3 divided by 1 from this list. And then if those don't work, then unfortunately I'm going to have to move to testing fractions. Hopefully we won't get to that point, though. We'll hopefully get down to a quadratic before then, and then maybe we'll get some of those fractional answers from factoring the quadratic. So let's go ahead and let's see if we can start by testing x minus 1. So I'm going to test x minus 1, okay, which means I'm going to put a 1 in the box. And then across the top here, we'll go 6, 13, negative 17, negative 5, and 3. Okay, so let's try our synthetic. 6, 19. Add these, we get 2, negative 3, and negative 3. That gives me 0. Hey, perfect. Okay, so right off the bat, I got x minus 1 to work. So let's collect our thoughts here. Let's see where we're at. So we got x minus 1. Okay, and then we got this remaining answer here. So let's think about this. Remember, this was an x to the fourth, I believe, which means we're going down in power here to an x cubed. So this is going to be 6x cubed plus 19x squared plus 2x minus 3. Okay, and then we want to continue seeing if we can factor this. Now, again, you could try grouping here, but I'm just going to tell you this cannot be factored by grouping. So that means we're going to have to do synthetic division more than once. We want to get this down to a quadratic, and currently it is not at a quadratic. So you have a couple options here. You could either try x minus 1 again, or if you wanted to, you could just keep moving on with your list. You do not have to create another list here. You are good to go as is, and you can just pick up where we left off with our rational root theorem. So don't forget about this x minus 1, but we are going to see what we can do with this remaining polynomial right here. So I'm going to go ahead and just move on. I'm going to try x plus 1. Which means I put a negative 1 in the box. So that would be 6, 19, 2, negative 3. This would be 6, negative 6, 13, negative 13, That's negative 11 and 11, and I can tell this is a no. Okay, so that's not going to work. So I don't want to try, or I definitely am not going to get an answer from x plus 1. Now remember, a lot of students, if they're just blindly doing this without putting any thought or effort into thinking about it, and what the rational root theorem means, is they're going to test x minus 2 and x plus 2. I can tell you without a shadow of a doubt, those are not going to work because I cannot get an answer of x equals 2 or negative 2 from this list right here. So I'm going to skip over those entirely. And the next thing I'm going to test with is I'm going to test with x minus 3 because that's the next easy rational root that I can get from my list. So I'm going to go with a 3 in the box, 6, 19, 2, negative 3. And let's try here. So this is going to be 6. It's going to be 18. That's 37. And I'm just going to say, nah, I can already tell these numbers are getting a little too large for me. So I can tell that x minus 3 is definitely not going to work here. And you can say, and if you see this as you're going through a problem, you don't have to go all the way. You can just stop. So it looks like x minus 3 not going to work. Hopefully x plus 3 works, because if not, we're going to have to venture into the land of testing fractions. Hopefully we won't get to that, but let's give it a shot. So that would be a negative 3 in the box. 6, 19, 2, and negative 3. Okay, 6, negative 18, 1. So we're keeping the numbers a little smaller here. That looks good. Negative 3, that would be a negative 1. And negative times negative gives me a positive. And yeah, I do get one that works right here. Okay, so once again, let's collect our thoughts. Let's see where we're at. Number one thing I see students miss: do not forget about this original thing, original factor we divided by. So we divided by x plus 1. Sorry, x minus 1, and it worked. Okay, so x minus 1 worked. Then we divided by x plus 3, and that worked. And then we had this remaining answer here. This was an x cubed, so this becomes an x squared. So this is 6x squared plus x minus 1. Okay, and I'm, as I expected or was hoping, down to a quadratic. So I'm going to see, can I factor this quadratic? So let's give it a shot here. Remember, if it's a 6x squared, my method of factoring, I'm going to put a 6x into 6x. Okay, take the first number, multiply by the last. So 6 times negative 1 is negative 6. Two numbers that multiply to give me negative 6, but add together to give me that positive 1 in the middle would be 3 and negative 2. Okay, so it's going to be a plus 3 and a minus 2. Now, I do need to divide a 6 out of all of this. Okay, now what you'll notice is, and the reason why is because 6 times 6 is 36, but I need it to be a 6 here. And so what you'll notice here is I can't divide either one of these sets of parentheses by 6 entirely, but what I can do is I can divide this by 3 and this by 2, and you'll notice that 3 times 2 is 6. So I really am dividing a 6 out of here. It's just coming in two separate steps. Okay. All right, let's do that, and then we should be completely factored, and we can sketch our graphs. This would be x minus 1 times x plus 3. Then I will have 2x plus 1, 6 divided by 3, and 3 divided by 3. And then I'll have 3x minus 1, 6 divided by 2, and 2 divided by 2. And that is looking good. Okay, so let's go through multiplicity. Let's think. 1, 1, 1, 1. Add them all together, I get 4, and this function is positive. Okay, does that match up with what we started with? Of course it does. We've got a 4 here, and this is positive. So in this case, we are even and positive. That's up and up. Okay, for my x-intercepts, set each set of parentheses equal to 0 and solve for x. That gives me 1, negative 3, negative 1/2, and 1/3. What you will notice is, if you think about that original list, let's bring it over here, double check all my work here. Checking our work is smart, very good life skill. Let's see, here are all the possible rational roots. Everything you get as an answer when you're done should show up in this list. 1 and negative 3 definitely show up. You'll notice that 1/2 shows up here, 1 divided by 2. And you'll also notice that 1/3 shows up here, 1 divided by 3. So everything is matching up here. I think I'm doing a pretty good job on my work. Matches up with the rational root theorem. And now I can graph. So I've got negative 3, negative 1/2. Let's see, positive 1/3 and positive 1, putting those in order. In behavior here is up and up. All of these are to the first power. So I'm going to go straight through at each one of these. Okay, pretty easy graph here, and we get this W shape when we are done. So this is probably about as difficult as I can make of one when it comes to the rational root theorem. And so we're following all our steps to create that list, test these numbers, see what gives me a range of 0. Big thing I wanted us to notice on this one, guys, is if there's no 2 at the top of this list, there is no reason to test x minus 2 and x plus 2. Okay, so just kind of showing you that here on this problem, and we get this final graph when we're done. Okay, so hopefully this is all clicking for you. One other thing that I want us to try, okay, and I will put a practice question in the OneNote folder for you, just like this. And whatever remaining time you have in class, if you want to keep working on that rational root theorem practice, you can, or you can go back and look at any of the other old notes. You can do that as well. We are going to call this is modeling. Modeling is typically when you look at a graph, you look at some sort of data, and you try to come up with an equation that fits that data. Okay, so fitting an equation to a graph, essentially. That's a very elementary definition for modeling, but that is exactly what we're going to do here in this problem. So here's what we're going to do. We are going to come up with the equation of minimum degree for the following function. Okay, so what I'm going to do here is I'm going to draw a picture, and then we are going to try to come up with an equation that matches this picture. Okay, I want you to pick some random stuff here. Let's go -7. Let's go -3/2. Let's go 0. Let's go pi. Let's go the square root of 17. And then let's go 31/5. Okay, so I'm going to pick some weird stuff here. And let's go like this. Let's go down on the left. Let's go down on the right. Let's bounce at -7. Let's go through at -3. Let's bounce at 0. Let's go through at pi. Let's bounce at the square root of 17. And then let's bounce at 31/5. Okay. All right. So taking a look at this graph. First of all, what I want us to focus on is what does this mean when it says minimum degree? Okay. Well, minimum degree means there's only 2 options for every x-intercept. If an x-intercept goes through, the minimum degree needed to go through an x-intercept is 1, and the minimum degree needed to bounce at an x-intercept is 2. Okay, because to go through, we need to be odd, and to bounce, we need to be even. Okay, so we know that we only really have 2 options when we come up with each factor right here when we write our equation. Another thing that I think is important on these problems is to note the end behavior. The end behavior of this graph is down, down. This only comes from a function that's even and negative. I'm really saying this to focus on this negative here, because when you start to write your answer for this, so let's say we want to start to write our answer here. If the function needs to be negative, well, the very first thing I'm going to do here is I'm going to put a negative at the front of the function. Okay, so I know this thing is even and negative because of its end behavior, so this function has to have a negative at the beginning. From here, though, I can just kind of start using reverse thinking to figure out these x-intercepts. So this is in my -7. Well, how would I get that? Only if one of my factors was an x plus 7. How would I get a -3/2? Well, to get a -3/2, I would have to subtract 3, and I would have to divide by 2. So this has to be a 2x plus 3. How would I get a 0? Well, that would be if I just had a standalone x. How would I get a pi? Well, that would be an x minus pi. How would I get a square root of 17? Well, that would be an x minus the square root of 17. And then how would I get a 31/5? Well, that would be from me adding 31 and then dividing by 5. So I'm just thinking in reverse here. So I'm getting all my x-intercepts listed. And then last but not least, I'm doing minimum degree, which means if I go through, I got to have an exponent of 1. And if I bounce, I have to have an exponent of 2. So I'm just going to go through each one here, and I'm going to put on my exponent. So this is going to be 2, because I bounced at -7. I went through here. I bounced at 0, so that would be 2. I went through at pi. I bounced at the square root of 17, and I bounced at 31 over 5. So when I'm finished, here is my final equation for this function of minimum degree. And if you just want to check, we said earlier that the multiplicity on this function had to be even because of the fact that I was going down, down. I'm just going to check here. I've got a 2, a 1, a 2, a 1, a 2, and a 2. And if I add all these together, that's 3, 5, 6, 8, and 10. And that checks out because that is even. And as mentioned, my function is negative, which is going to create that end behavior of down, down. Okay, so this is just called modeling. This is kind of thinking in reverse. I just wanted to finish this unit kind of talking about this. Just kind of bring us back to the basics of these functions, but it's thinking about them in a little bit different way. I will put a practice question like this in the OneNote folder, and I hope to be back with you guys pretty soon. Remember, we got a quiz coming up here for our next class. But I will let you guys work together on that, and you can use any written notes or written homework. You cannot be on your computer on the OneNote, but anything that you've written down, you can use that on that quiz. Missed you guys, and I'm looking forward to being back hopefully soon. And you guys take care, and we'll talk to you later. Bye.